Okay, in this video we are going to look into building an electronic interface to trigger and fire a spark plug for testing and development. Now we're going to be using one of these. This is a coil pack. Now this is out of an Audi A5 3.2 liter. And these are sometimes called COPs, Coil Over Plug, because the coil that's inside the shaft fits over the spark plug, which is down at the bottom. Now inside here there's also some electronics. You can see there's 4 terminals in here. And we're going to build this interface, electronic interface, that we could feed into this connector so we could fire this spark plug. Okay, if you owned a car in the 70s or the 80s, you would probably have a setup similar to this, where you have a single coil and it's feeding the high voltage pulses into the center of this distributor cap, and then a rotor inside the cap will distribute that pulse to each of the spark plugs. So inside here we can see the rotor, which would be spinning around and feeding the high voltage to each of the spark plugs as it turns and is driven off the camshaft of the car. Okay, so now the modern cars today have a coil for each spark plug, similar to this coil pack, and they're controlled by the onboard computer, the ECU, through this connector. Now I have built a little test device that will actually test these coil packs as they're running in the car. It detects the magnetic field given off by the coil when the spark plug is fired. So that verifies the signal from the computer is getting to this connector, and it's actually firing the coil, but it doesn't actually test if the spark plug is sparking, because you could have a broken wire in between the coil and the spark plug. So with this little interface we're going to build that will hook up to this connector, we could actually see the spark on the spark plug, and we know the coil pack is working properly. Okay, the first circuit that we will look at will be very simple. There will be no microcontroller. There will be no code, and we'll be using the common 555 timer, which you can see on my breadboard. Now the 555 timer can source and sync 200 milliamps. That's enough to drive this coil pack. Now inside this coil pack there's an IGBT, an insulated gate bipolar transistor, and the IGBT has a front end of a MOSFET and a back end of a bipolar transistor for high current and high voltage control. So we'll be sending 5-volt pulses into this connector, and the duration of this pulse will be 3 milliseconds, and that will give them enough time for the primary coil to reach its maximum current flow and magnetic field strength. Now this pulse width is called a dwell, and that's the amount of time the primary coil is energized. And then when the coil is de-energized, the magnetic field will collapse and we'll get a high voltage in the secondary of the coil, and then we'll see a spark on the spark plug. Now the spark energy does not increase when we increase the dwell past its maximum value, because we'll saturate the core and we'll just heat up the transformer. So normally when the engine is running, we'll have a dwell of 3 milliseconds, and while it's cranking, while we're starting it, it'll probably be around 4 milliseconds because the voltage of the battery will drop. Okay, I have my trigger circuit connected up to my coil pack, and you can see my LED, which is flashing. Now it's flashing at 8 Hertz, 8 times a second. Now the camera isn't picking it up properly, but it's flashing continuously. So when I energize the coil pack, when I feed it 12 volts, we'll actually see the spark, and the spark will match the LED, so the spark will be at 8 Hertz, which will be around 1,000 RPM on the motor. That's just above idle. So I'll connect up the power to the coil pack, and you can see the sparks happening. That's at 8 Hertz, so that's 1,000 RPM. And if we look at the scope, we can see the pulse width of the pulse that we're feeding the coil pack, the 5-volt pulse, is around 3 milliseconds in duration. That's our dwell. And if we zoom back, we can look at the frequency, and it's around 8 Hertz, which is 1,000 RPM. So our next circuit will involve a microcontroller, where we could actually control the dwell, which will be variable, and we could control the frequency of the spark, so we could control actually the RPM range. Okay, your vehicle engine is a 4-stroke engine. It has 4 cycles. It has an intake, compression, power, and exhaust, and it takes 2 revolutions of the crankshaft to complete this sequence of 4 cycles. So there is 1 spark generated for every 2 revolutions of the crankshaft. So if our engine is revving at 1,000 RPM, that's 500 sparks per minute. So 500 sparks in 60 seconds, that's 8.33 sparks per second. So it's 8.33 Hertz, and that'll give us 1,000 RPM. Now we can calculate that for 5,000 RPM. That's 2,500 sparks per minute. That'll give us 41.66 Hertz. That's 41.66 sparks per second. And that'll give us our RPM of 5,000. So when we build our microcontroller trigger circuit, we'll be able to control the RPM, the spark frequency, from 41.66 for 5,000 RPM, and we could bring it down to 1,000 RPM to set our spark at 8.33 Hertz. Okay, here's a very simple schematic diagram of our coil pack. So inside the coil pack we have an IGBT, an insulated gate bipolar transistor, and the coil, and they're both located near the top of the coil pack itself, near the connector. Now the coil has two windings. It has a primary winding and it has a secondary winding, and the primary winding is controlled by the IGBT. So when our trigger voltage, our 5-volt pulse, goes high, it's going to turn on the transistor. We're going to have current flowing from the 12-volt power supply through the primary winding through the transistor to ground. Now that's going to create a magnetic field in the primary winding after 3 milliseconds. That's our dwell time. Now after 3 milliseconds, the voltage, our trigger voltage, will drop to 0. We'll turn off the transistor. It will de-energize the primary coil, and the magnetic field will collapse. Now that collapsing magnetic field will induce a very high voltage in a secondary, which is fed to our spark plug, which will generate a spark. Okay, here's the schematic diagram of the 555 timer trigger circuit for a coil pack. So the components on the left will determine the waveform output on pin 3, which will give us a 5-volt pulse of 3 milliseconds for a dwell time, then a pulse train of 8.33 Hertz for a frequency of 1,000 RPM. Now the charge time for our 3 millisecond dwell time is our 8.2 k ohm resistor through the diode, charging up the 0.47 microfarad capacitor. Now after 3 milliseconds, it's going to trigger the 555 timer on pins 2 and 6. Pin 7 will go to ground and now discharge the capacitor through the 330 k ohm resistor, and that will give us our frequency of 8.33 Hertz. So you could play around with these components to come up with your own frequency for your dwell time and your RPM. Okay, if you have a look at the connector on the coil pack, you can see it's labeled 1, 2, 3, and 4. So pin 1 is your positive 12 volts, that's your battery. Pin 2 is signal ground. Pin 3 is trigger, so that's the pulse train from the 555 timer trigger circuit. And pin 4 is the power ground. So they separated the power ground and the signal ground, so there wouldn't be any ground loops. So you could connect pins 2 and 4 together, and that's your common ground. Apply plus 12 volts to pin 1, and then pin 3 is your trigger input from the 555 timer. That's your pulse train. Okay, I have my Nano connected up to my coil pack, and I'm running a program where I could actually change the dwell time and the frequency by using my up-down keys, so it's variable. So right now you can see I have 2 milliseconds for dwell time. Now I could increase it up to 4 milliseconds. Now for the frequency, I'll apply power to the coil, and it'll be running at 5,000 RPM, and I'll take it down to 1,000 RPM. So that's 5,000 RPM. Now with my keyboard, I'll take it down . Now we're down to 1,000 RPM. So I have total control of the RPM and the dwell time with the Nano and using my keyboard. Okay, here's the schematic diagram of the driver that I use with my Nano to drive the coil pack. Now normally I would use a TC4424 driver IC. They're very handy, but you probably don't have one in your parts bin, so I use this circuitry here. It's very easy to build. You probably got the parts for it. Got an NPN and a PNP transistor, a 2N2222 and a 2N3906. And I configured it as emitter followers, so you got a good drive. So the positive drive comes from the NPN, and a negative drive is from the PNP. So you hook up pin 9, which I was using on my Nano for my pulse train output, to this input here. It'll drive the driver, which will drive the coil pack properly. Okay, so that was my little tutorial on how to drive a coil pack, either with a 555 timer, a simple circuit, or using a microcontroller, more advanced. Now there's other coil packs out there. This one comes off an Audi, and there's all kinds of other ones out there that you could use. Some use a negative going pulse to trigger it, so you have to look at the specs. But this will get you started on how to interface to a coil pack for troubleshooting or to design your own ignition system.